Experiments can often be expensive and challenging to do, so sometimes instead of actually carrying out an experiment, we can simulate an experiment using the laws of probability. So in this section, that's what we're going to take a look at. How can we use the laws of probability in order to simulate specific experiments? So in this section, you're going to be able to understand what a long-run relative frequency is. We're going to use a simulation to model chance behavior, which is basically like carrying out an experiment. We often want to run an experiment, but it can be costly and time-consuming. So here's where we're going to discuss how we can simulate a real-life experiment without actually conducting the experiment ourselves. So idea of probability, we're actually going to be going into probability into Unit 5. So into Unit 4. So this section, we're just going to get a general idea of probability. So probability is basically chance behavior. Chance behavior is often unpredictable in the short run. So if you flip a coin 10 times, you could potentially get tails every single time you flip a coin. However, it is relatively predictable in the long run. It has a regular, predictable pattern in the long run. So long run, what does that mean? If I were to flip a coin 1,000,000 times, hopefully, when I flip it 1,000,000 times, due to the probability that you have 50% to get tails and 50% to get heads, that in the long run, you would get about half of those flips would be tails. All right, so what I just talked about was the law of large numbers. The law of large numbers says that if we observe more and more repetitions of a chance process, the proportion of times that we actually perform that experiment will approach a single value. So if I flip a coin 8,000,000 times, if I repeat that same thing over and over again, it's going to approach a single value, or I'll get about 50% heads and about 50% tails. So basically what this tells us is the more trials you do, the closer to the theoretical probability matches the empirical probability. Empirical probability is you actually sitting there and flipping the coin. Okay, so when you actually sit there and flip the coin many times, hopefully the probability of you getting heads and tails is going to end up being 50-50 rather than if you do it 10 times. So law of large numbers tells us what happens to the probability over the long run. So here's just an example. Let's just say I flipped a coin and I'm looking at the proportion of heads that I get in my coin toss. All right, so notice if I flip it only 4 or 5 times right here, my proportion is only about 40% that I'm getting heads here, 50%, we're at 50%, but it's kind of all over the place. However, in this case, I flipped it 500 times. So notice it's much more variable, but it's getting closer, it's converging to one number, about 50%, the more times that I flip the coin. So like I said, it tells us what happens in the long run. So if I repeat this process over and over again, what's going to happen to the probability? All right, so probability, what exactly does probability mean? So this is just a very brief introduction. We'll take a look at this more in later sections. The probability of any outcome is the chance process is a number between 0 and 1. It describes the proportion of times the outcome would occur in a very long series of repetitions. So when we say, what's the probability I roll a dice and get a 6, is 1 out of 6. All right, so it's going to, if I were to roll a dice 500 times, most likely 1/6 of the time I would roll a 6. And the probability between 0 and 1, 0 is that I don't get a 6. 100% is that I do get a 6. Okay, so probabilities are always between 0 and 1. What does it mean to interpret probability? So what are we talking about when we say interpret the probability? In the long run, what is the relative frequency? After many rolls of the dice, what's the probability that you roll a 6? What do you predict will happen? Well, hopefully it should be about 1/6. What is the probability of rolling 2 die and getting a sum of 7? What would it mean to interpret this value? Okay, so just remember this is always in the long run. So here's a table. Okay, so we're not going to just say the probability of rolling 2 die and getting a 7, getting a sum of 7 is 6 out of 36 or 1/6. It's in the long run. So if 2 die were rolled many times, we would expect a sum of 7, 6 out of 36 or 1/6 of the time. And this is all the possibilities here. If I roll 2 dice, there's 36 possibilities. All right, so the idea of probability is pretty straightforward, but there's a couple myths of chance behavior that we just need to address before we move on. The idea of probability is that randomness is predictable in the long run. So our intuition tells us that random phenomena should also be predictable in the short run. However, keep in mind that probability does not allow us to make short run predictions. It only allows us to make long run predictions. So if we roll a die 10 times and get a 3, okay, 50% of the time, it doesn't necessarily mean that if you roll the dice again, that you're more likely to get a 3 on the 11th roll. You still have a 1/6 chance of getting a 3 on the 11th roll. So people would say, "Oh, I'm on a streak." You know, they're gambling and they're on a streak. They say, "I've rolled a 3 50% of the time. That means I'm going to continue to roll a 3." No. Every time you roll that dice, it's still a 1/6 chance of getting a 3. The long run predictions haven't played out yet because there's not enough trials. Not predictable in the short run. Okay, the biggest mistake is to apply the law of large numbers to too small of trials. So like I said, this has to be many, 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 many trials before we can apply the long run probabilities. So what do we mean when we say the law of averages? What is the law of averages? Probability tells us that random behavior evens out in the long run, that future outcomes are not affected by past behavior. So that's sort of the law, that's kind of like your law of large numbers, that the probability of rolling a die in the long run, if I do it many, many, many times, is going to be 1/6. And whatever you rolled in the past, if you rolled 6 sixes in a row, the next roll that you do is not affected by the fact that you just rolled 6 sixes. Okay? Past outcomes don't influence the likelihood of an individual outcomes occurring in the future. So that just means, like I said, you roll a dice, you roll 6 sixes in a row. Those 6 sixes are completely out of the picture. You still have a 1/6 chance the next roll of getting a 6. Okay, so streaks, this is what I was talking about on the previous page, don't influence future outcomes. If you roll a die and get a 6 5 times in a row, it doesn't mean you're more likely to get a 6 in the future. It's still the same probability because it's talking about the probability in the long run of rolling a 6 when you roll a die. All right, so let's just take a minute and look at Joe DiMaggio's hitting streak. All right. In this article, the authors claim that one of the most remarkable streaks in baseball history was Joe DiMaggio's 56 consecutive game hitting streak. However, it wasn't very remarkable at all. Why? Obviously, it's extremely unlikely for a particular individual to have his hitting streak that long. But when we considered all the players in all the seasons of baseball history, we should expect some unusual performances every now and then. To investigate, what we did is we simulated the performance of every baseball player in every season a total of 10,000 times. In each of those 10,000 simulated histories of baseball, they recorded the longest running streak. So in 42% of those trials, someone had a hitting streak of at least 56 games in a row, with the longest being 109 games in a row. So that's basically like saying, if I took all these baseball players and I had them continually play for 10,000, total of 10,000 times up at bat, in 42% of those, they would have a hitting streak of 56 games in a row. So it wasn't as remarkable as everyone said it was going to be. All right, so why do we do simulations? So what we just talked about on the previous page with Joe DiMaggio was a simulation of putting players at bat to see what percentage they would have of getting that hitting streak of 56. So the imitation of chance behavior based on a model is called a simulation. So on the previous page right here, when they simulated performance, they basically pretended like somebody batted 10,000 times and then saw out of those 10,000 times, how many times did they get 56 hits in a row? All right, that simulation, we didn't actually go and take baseball players and have them bat 10,000 times. We used models in order to make that prediction. All right, so why do we perform simulation? Number one, we perform simulation to estimate probabilities when the theoretical probabilities are too difficult to estimate. All right, so that's basically like just saying that if I'm walking down the street, what's the probability of meeting someone with red hair? You actually cannot go down every single solitary street and find the probability of getting someone with red hair. So we'd use a simulation in order to estimate the probability of people with red hair. It's easy to estimate probabilities with cards, die, and coins. It gets more difficult when you're using sort of real life situations. So an example, what's the probability that an AP Stat student in Fairfax County is taller than 6 feet? Is it really practical to get a simple random sample of every single solitary student in Fairfax County and then figure out how many of them are taller than 6 feet? Okay, another one is, what's the probability that when you go to McDonald's that you're going to get the toy that you want? Okay, so what exactly is that probability? A simulation is going to make this easier to do. It's basically like a mock trial of what will happen over time. All right, so like I said, the imitation of chance behavior based on a model that accurately represents a situation is called a simulation. All right, so how do we do a simulation? There's 4 steps you're going to look at, and we're going to use these again in the future. So get used to saying state, plan, do, conclude. State, plan, do, conclude. So state, the first portion that you're going to do is state the assumptions about chance behavior. So what do you know about the probabilities that are occurring? Okay, what are the probabilities related to each individual situation? Are the trials independent of each other? So when I roll a die one time, is that going to affect how I roll it a second time? No, the trials are independent of each other. Plan describes how you're going to use chance to imitate one repetition of the process. All right, you're going to tell what you will record at the end of each repetition, and you're going to assign digits to represent outcomes. I know this is confusing when you're first looking at this. It's much easier when you look at an example. Okay, so basically, you are assigning numbers to represent chance. All right, please take a look at this template right here. You're going to use this, okay, in order to help to plan how you're going to perform your simulation. So starting at, we'll use a number table, starting at line, say 103, on the random integer table, you're going to read every 1, 2, or 3 digits. We're going to select the digits that fall between 1 and 5. You always omit 0, 0 because they usually don't represent anything, and repeated numbers. Sometimes you won't omit repeated numbers. If we were talking about the baseball example, we'd say record whether it's a hit or not hit, okay? Identify the stopping point. So after we've had 10,000 hits, or after you've picked 4 hotels. All right, like I said, I know it's kind of confusing to see on here, but once we put a problem together, it'll make more sense. All right, then do is basically you doing the simulation. Perform many repetitions of the simulation. So if you're simulating 10,000 bats for each baseball player, you don't just want to do 3 of them. You want to maybe do 10,000 bats for 15 baseball players. And then you're going to conclude, you're going to use the results of your simulation, look at the probabilities that you got from your simulation to answer the question of interest. So we're basically interpreting our results. So was it unusual that he got a 56 hitting streak? Well, based on our simulation, it really wasn't that unusual. You're basically telling the reader what you found from your simulation. Now, here's the tricky part. Make sure you state the probability you got from your situation or simulation in context of the problem. Then you want to make sure you state whether or not the probability you started with was reasonable or not. All right, so you're doing a conclusion based on your simulation, and then you're deciding, hey, was the probability I got, was that reasonable? Did that make sense? All right. And then what do we necessarily use for a simulation? How can we use a simulation? We'll often use random numbers or random integers from your graphing calculator or some sort of technology to perform simulations. So go ahead and take a look at the next recording to show how to perform a simulation.